Okay, what I wanted to do next was to explore what some of these orbits actually look like. And so let's just go up to the data projector for a second, and we'll see what this 2s orbit looks like. Notice here it's spherically symmetric, so there's no angular dependence. Here you have a 2p orbit, okay, because L equals 1. In this case, m sub L equals 0. So this corresponds to a figure 8 of revolution, which the electron spends half its time up in this lobe, half its time down in that lobe, but no time at the point that joins the two. Okay, and so as a particle, that wouldn't make any sense. How could it spend half its time here, half its time there, and never any time at the point that joins the two? And we can't answer that if it's a particle, but if it's a wave, it can cancel out. So this is like a three-dimensional wave pattern that we're looking at here, but it's a probability wave, and so this is all very weird. And so then we also have the two other p orbits that correspond to m sub L equals +1 or -1. So these are figure 8s of revolution about the horizontal axis rather than about the z-axis. Now if we go back to this problem, this actually corresponds to a completely different kind of orbit than what we've been talking about so far. Because here we can have 5 different possible configurations for the angular momentum quantum number. But remember that each one of those can be either plus or minus 1/2. And so this would be the case then if n equals 3 and L equals 2. And so in that case, m sub L can be -2, -1, 0, +1, or +2. And our different psi values for that would be psi of 3, 2, 0, +1/2, because one of these has to be spin. Then I'll just reproduce that down here with -1/2. Okay, so this is with the m sub L equals 0, but with L equals 2. So I'm just taking care of this one now, here. So it's taken care of. Now I can do the next one. 3, 2, 1 +1/2. And psi of 3, 2, 1 -1/2. So that takes care of this one. Then I can do psi of 3, 2, 2 +1/2. And here I can do psi of 3, 2, 2 -1/2. That takes care of this one. So I still have these two to take care of. So this would be psi of 3, 2 -1 +1/2, and psi of 3, 2 -1 -1/2. Then finally this one here. That's going to be psi of 3, 2 -2 +1/2, and psi of 3, 2 -2 -1/2. So if we count these up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got, well, these are called d orbits. Okay, so the d orbits have kind of weird shapes. Here we can see some of the d orbits for here. This would be n equals 3. Here's the L equals 1, 1 that we looked at before. Okay, and here, for this n equals 3, then L can be 1. So this is a d orbit. Here we've got n equals 3, L equals 2. We can see that these two are kind of fitting together almost like an origami puzzle, so that these different values for the possible probability distributions will fit into each other and make a perfect sphere. If you add up all of the different d orbital shapes, they will add up and create a perfect sphere, which is kind of an interesting symmetry, so that we can only really separate them by projecting that magnetic field. That's how we can determine whether or not these orbits are just a nice idea or whether they actually have something that's measurable about them that can be determined. Okay? and so if we go back to the periodic table then, what we see is that these d orbits extend all the way across in the middle. Okay, so this would be a d orbit all the way to here. There's 10 of these. 3, 4, 5, 6, 7, 8, 9, 10. And so a completed then 3D orbit would be what we could call here 3D10. Okay, because this is in the n equals 3, even though it's in the 4th row. So we want to be careful with that. The rows don't always correspond to the n values. When we start getting to d orbits, they get shifted down one. So they're actually in the 4th row, but they're still part of the n equals 3 possibilities. Okay, and so for n equals 3, then you see that we've got 3s2, 3p6, 3d10. Okay, so we have here 10 and 6 is 16 plus 2 is 18. So the number of states in the n equals 3 is 18. What about the number of states in n equals 2? Well, then we have the 2s2, 2p6, and so the number of states there would be 2 plus 6 is 8. How about for n equals 1? The number of states here is just going to be 1s2. So we end up with just 2 states. So you notice then that the total number of states that we get as a function of the n value can be written as 2 times n squared. So here then, for n equals 1, that's going to be 2 times 1 squared is 2. For n equals 2, this will be 2 times 2 squared, which is 4. 4 times 2 is 8. And for the n equals 3 state, this will be 2 times 3 squared, which is 9. 2 times 9 is 18. So this then fills out the structure of the periodic table in terms of allowed quantum numbers that we get from solving the Schrodinger equation. Now, are these orbits real? Or is it just a great idea? And it turns out that they're real. And in section 4.4, we will go back, 41.4, we'll go back to this after the midterm, and we'll look at the Zeeman effect. So we'll do this later. So this will give us proof of the existence of these orbits. That it's a little more mathematical than what I wanted to get into now. So 41.4 then, this is I think 2 E's in Zeeman and 1 N, something like that. I'll come back and check that later. That is something that you don't need to worry about for the quiz or for the midterm. But I would like you to try to come up to speed in terms of the different n, l, and m sub l values and how they all work together to give us the structure of matter on the periodic table. One more thing I wanted to mention is that as we go up, and if we could just look at the periodic table one more time, as we go up to higher values of n, we would think that these would be at a lower energy state, and yet the filling order is such that the 3D orbits come in before the 4s orbits. So why is that? Well, it turns out that there is such a thing as shielding, and shielding prevents the electrons from feeling the effects of filled electron shells that are closer in. And so something that is out farther, having more angular momentum, can end up in a lower energy state than something that is at a higher value of n. And so I'll go into that more after the midterm.